Assalamualaikum everyone and very good day to all. In this video, we'll continue learning about digital to digital conversion techniques, which in particular we are using block coding and redundancy. Here is the table of contents for you to navigate through this video. So as we saw from previous chapter, we discussed about data and signals, and data can be either digital or analog. Same goes to signals. It can be represented, it can be representing data in terms of digital or analog. In this chapter, we will see how we can represent digital data by using digital signals. There are basically three different techniques for the conversion, and they are line coding, block coding, and scrambling. Line coding is always needed, whereas block coding and scrambling may or may not be needed. Okay, let's go to block coding. As you can see from previous videos, we need redundancy to ensure synchronization and also to provide some kind of inherent error detecting. And block coding can give us this redundancy and also improve the performance of line coding. In general, block coding changes a block of m bits into a block of n bits, where n is larger than m, and block coding is referred to as MB/NB encoding technique. The slash in block encoding, for example, 4B/MB, it distinguishes block encoding from multi-level encoding that you saw in previous video, for example, 8B60, where it is written without a slash. And block coding normally involves three steps: division, substitution, and combination. In the division step, a sequence of bits is divided into groups of m bits. For example, in 4B5B encoding, the original bit sequence is divided into 4-bit groups. The heart of block coding is the substitution step. In this step, we substitute an m-bit group with an n-bit group. For example, in 4B5B again, we encoded a substitute of a 4-bit group with a 5-bit group. Finally, the n-bit groups are combined to form a stream. The new stream has more bits than the original bits, and as you can see in the next figure, as you can see on the figure on the left here, the flow of block coding where we have division and then substitution and then combination. I have a video here for you to watch where we have original bit sequence divided into m bit groups, and then it's substituted with n bit group, and then finally it is combined to form a stream, and the stream has more bits than the original bits. Block coding 4B/5B, or also known as 4 binary/5 binary coding scheme, it was actually designed to be used in combination with NRZ invert or NRZI. If you remember that NRZI has a good signal rate, that is 1/2 of the biphase, but it has a synchronization problem where a long sequence of zeros can make the receiver clock lose synchronization, but it has no problem with long sequences of ones. Okay, one solution is to change the bit stream prior to encoding with NRZ invert so that it does not have a long stream of zeros. So the 4B/5P scheme, it will achieve this goal where the block coded stream does not have more than 3 consecutive zeros. As you can see in the figure, at the receiver, the NRZI encoded digital signal, it is first decoded into a stream of bits and then decoded to remove the redundancy. Okay, what does it mean by will not have more than 3 consecutive zeros? This is because the 5-bit output that replaces the 4-bit input has no more than one leading zero on the left bit and no more than 2 trailing zeros on the right bits. So when different groups are combined to make a new sequence, there are never more than 3 consecutive zeros. In this table, you can see the mapping codes of 4B/5B. So it shows the corresponding pairs. And note that the first two columns pair a 4-bit group with a 5-bit group. So a group of 4 bits can have 16 different combinations, while a group of 5 bits can have 32 different combinations. How can we get that? It's 2 to the power 4 and also 2 to the power 5, respectively. And this means that there are 16 groups that are not used in 4B/5B encoding. And this is what we call redundancy. And some of these unused groups are used for control purposes, and the others are not used at all. Okay, the latter provide a kind of error detection. And if a 5-bit group arrives that belongs to the unused portion of the table, the receiver would know that there is an error in the transmission. In this figure, it shows an example of substitution in 4B/5B coding. 4B/5B encoding solves the problem of synchronization and also overcomes one of the deficiencies of NRZ invert. However, we need to remember that increases the signal rate of NRZI, the redundant bits at 20% more baud. Still, the result is less than the biphase scheme, which has a signal rate of 2 times that of NRZI. However, 4B/5B block encoding does not solve the DC component of NRZI. If a DC component is unacceptable, we need to use biphase or bipolar encoding instead. Okay, let's do an example on block coding 4B/5B. Let's say we want to send data at 1 megabit per second rate. So the question is, what is the minimum required bandwidth if you are using a combination of 4B/5B and NRZI? Or what is the minimum required bandwidth if you're using Manchester coding? So if we use the 4B/5B block coding, it increases the bit rate to 1.25 megabit per second. And the minimum bandwidth using NRZI is n/2, so you have that bit rate 1.25 megabit per second to 625 kilohertz. And whereas the Manchester scheme needs a minimum bandwidth of 1 megahertz, so the first choice, the 4B/5B combined with NRZ invert, it needs a lower bandwidth but it still has a DC component, whereas the Manchester scheme, it needs a higher bandwidth but it does not have a DC component. Let's see another block coding, that is the 8B/10B, or also known as 8 binary/10 binary. This is actually similar to 4B/5B encoding, except that it is now 8 bits of data is substituted by a 10-bit code. It provides a greater error detection capability if compared to 4B/5B, and the 8B/10B block coding is actually a combination of 5B/6B and 3B/4B encoding as shown in the figure. The 5 most significant bits of a 10-bit block are fed into the 5B/6B encoder. The 3 least significant bits are then fed into a 3B/4B encoder. The split is done to simplify the mapping table and to prevent a long run of consecutive zeros or ones. So the code uses a disparity controller which keeps track of excess zeros over ones or ones over zeros, and if the bits in the current block create a disparity that contributes to the previous disparity in either direction, then each bit in the code is complemented. Okay, 0 is changed to 1 and a 1 is changed to a 0. The coding has a 2 to the power of 10 minus 2 to the power of 8, which is equals to 768 redundant groups that can be used for disparity checking and error detection. In general, this technique is better or superior to 4B/5B because of the better built-in error checking capability and also better synchronization. From what we've learned in line coding schemes, we see that each of these schemes, they have their own advantages and disadvantages. Like for example, in biphase schemes, that kind of scheme is suitable for dedicated links between stations in a LAN, but it is not suitable for long distance communications because of their wide bandwidth requirement. And also, as we saw in combination of block coding and NRZ line coding, this combination is also not suitable for long distance encoding either because of the DC component. But bipolar AMI encoding, on the other hand, it has a narrow bandwidth and it does not create a DC component. However, in bipolar AMI, a long sequence of zeros will upset the synchronization. So if we can find a way to avoid a long sequence of zeros in the original stream, we can use bipolar MI for long distances. So in a way, we are looking for a technique that does not increase the number of bits and at the same time provide synchronization. So this solution basically is the one that substitutes long zero level pulses with a combination of other levels to provide synchronization. So this solution is called scrambling. We modify part of the AMI rule to include scrambling as shown in this figure. Note that scrambling as opposed to block coding is done at the same time as encoding. So the system needs to insert the required pulses based on the defined scrambling rules. Two common scrambling techniques are BAZS and HDB3. So BAZS, or the long name for it is bipolar with 8-0 substitution, is commonly used in North America. And in this technique, 8 consecutive zero level voltages are replaced by the sequence of 000V, B0V, B. So the V in the sequence denotes violation. This is a non-zero voltage that breaks an AMI rule of encoding where opposite polarity from the previous. And the B in the sequence denotes bipolar, which means a non-zero level voltage in accordance with AMI rule. There are two cases as shown in figure at the top. Note that the scrambling in this case does not change the bit rate. Also, the technique balances the positive and negative voltage levels where we have 2 positive and 2 negatives, which means that the DC balance is maintained. Note that the substitution also may change the polarity of a 1 because after the substitution, AMI needs to follow its rules. So in other words, B8ZS substitutes 8 consecutive zeros with 000VB, 0VB. One more point is that the letter V or violation or B bipolar here is relative, meaning that the V means the same polarity as the polarity of the previous non-zero pulse, and B means the polarity opposite to the polarity of the previous non-zero pulse. Another common scrambling technique is known as high density bipolar 3-0 or HDB3. It is commonly used outside of North America. In this technique, which is more conservative than BZS, 4 consecutive zero level voltages are replaced with a sequence of 000V or B00V. The reason for the two different substitution is to maintain the even number of non-zero pulses after each substitution. And there are two rules and they are stated as follows. If the number of non-zero pulses after the last substitution is odd, the substitution pattern will be 000V, which makes the total number of non-zero pulses even. And if the number of non-zero pulses after the last substitution is even, the substituting pattern will be B00V, which makes the total number of non-zero pulses even. Okay, so in this figure, as you can see, we substitute 4 consecutive zeros with 000V or B00V, depending on the number of non-zero pulses after the last substitution. So there are several points you need to mention here. First, before the first substitution, the number of non-zero pulses is even, so the first substitution is B00V. Okay, and after the substitution, the priority of 1 bit is changed because the AMI scheme after each substitution must follow its own rule. So after this bit, we need another substitution, which is 000V, because we have only one non-zero pulse, which is odd, after the last substitution. And the third substitution is B00V, because there are no non-zero pulses after the second substitution, which is even. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.